Hello, we're going to talk about some different classifications of functions. And the first classification we're going to talk about is one-to-one. Now, if something is one-to-one, that's something that passes. If it passes the horizontal, I'll just write horizontal line test. Alright, so if it passes the horizontal line test, that would be something like a linear function, right? And what does that mean? That means anytime I draw a horizontal line, it only crosses once every time I draw that, right? Hence, one-to-one. It only crosses once. Now, if something is what we call many-to-one, it's just something that does not pass the vertical line test. So something, not vertical line, that would be for a function, the horizontal line test. So I guess I could draw a few more for a one-to-one. Cubic functions are one-to-one, right? Just like that. That's one-to-one. That passes the horizontal line test. And root problems pass the one-to-one. But also linear cubic functions, not all cubics, not all root problems, but also rational functions that look like this pass the horizontal line test and are one-to-one. Now, many-to-one are functions that do not pass the vertical line test, like, for instance, quadratics. Quadratics do not pass, right? Quadratics do not pass. That is many-to-one. Certain cubics don't, right? If it looks like that, that does not pass the horizontal line test, and so on, right? So let's see some problems with this. Now, if we look at example 12, it says, which of the following functions are one-to-one? And which are many-to-one. So first one just gives you a set of ordered pairs, and you can see that at different x values we get the same y values, right? So I know that this one right here, A, is many-to-one. B, now this one here, let's see. It doesn't matter what happens with the x, but the y's all come out to different values. So this one's one-to-one. And this one here, now they got a graph, and right here, that one's many-to-one. And C, you can see there's nowhere, everywhere it crosses is one line, so this is one-to-one. Good? Alright, some more examples. Next type of classification we're going to talk about are even and odd functions. And here are what even and odd functions. Now, I drew an example of a quadratic, and this is an even function, right? And even functions are symmetric about the y-axis. So as long as they completely fold over and it's on top of each other, then that's what we call an even function. Now, odd function would be something like a cubic, or this is y equals x cubed, or something like it. Now, this has what we say is symmetric about the origin, or we can call it rotational symmetry. So it rotates 180 degrees, and it's the same function. Now, how we represent that algebraically is this way. So if we look at a function, an even function, a function is even if for all x in a domain, negative x is in the domain, and f of x is equal to negative f of x. So if we plug in a negative x into the function and it comes out to the same function, then it's even. Now, odd functions, when we plug in the negative f of x, it equals the negative of that function. And that's what even and odd functions will look like. So And you can see, kind of check even up here. If I put negative x squared in, if I put a negative x there, negative x squared is just x squared. I get the same function, hence even. And if I put a negative x in here, a negative x cubed is a negative x cubed, so I get the opposite of that, and that's an odd function. And you can see how that works. Now, let's look at some examples. And we're going to look at example 13, and it says, determine algebraically if the following functions are even, odd, or neither. Confirm your answer graphically. So, like we said before, you know, if it's an even function, if it equals, when we plug negative f of x, and it doesn't change the function at all, and odd if it becomes the opposite of that. But it's possible that it could be neither. So we'll start with the first one, a. So f of negative x is equal to negative 3 negative x squared plus 5, which is equal to negative 3x squared. That becomes a positive plus 5, which is equal to f of x. Therefore, even. Good? Now we can try, so that's for A. For B, it's given us g of negatives, gives us a piecewise function. Now, when I plug it in, I'm going to get a negative x minus pi, but my intervals will change. If I put a negative x and solve for it, I'm going to get a 0 is less than x is less than or equal to pi. Then if I plug in the other one, I'm going to get x plus pi is negative pi is less than x is less than or equal to 0. And we can see that's neither the same thing nor the negative of g of x, right? Because if we put negative into this, if it was negative g of x, we would have plus, and then this one would be a positive and a negative, so this one's therefore neither. Good? And then the last one, C, h of negative x, right? That's going to be equal to, well, when I plug it into there, I'm going to get a x minus pi squared when I factor out the negative and square it, and then I'm going to have 0 is less than x is less than or equal to pi. And then when I plug negative into here, I'm going to pull out the negative. Negative is going to stay there, but I'm going to be x plus pi squared is negative pi less than x less than or equal to 0. And this is equal to a negative, I should say a negative h of x, right? You can see that's the negative of that one. If I plug the negative in here, I get x minus pi from 0 to pi, and if I plug in negative to the bottom one, top one, I get a negative x plus pi squared from negative pi to 0. Sounds good? So therefore, this one is odd. Sound good?